Welcome back, students. This is the session 8 from the chapter about power and energy. And the today's topic is spring force and the potential energy of the spring. So, in this session, I will be discussing about the spring force, and we will also derive the potential energy uh, of the spring when it is extended by a certain displacement. So now in this case, the spring is we are considering the spring to be massless. Spring is massless, first thing, and I have drawn here three figures here. The first one, in the first this figure, this block and the spring system. This is a block which is attached to a spring. The one end of the spring is attached to a rigid wall, and the other end is connected to this block. Now this block is resting on a frictionless surface. Now, so this is the equilibrium position, and I have taken this horizontal surface to be the x-axis, and this is the y-axis, and this point is the origin. Okay, so this is the point of origin. Now in the second figure, that is, this is the, let's say this is the figure number 1, this is the figure number 2. Now in the second figure, this spring is displaced in the positive x direction. See here. So when this spring is displaced in the positive x direction, and let us say the displacement is xm, so this spring force will be acting in the opposite direction, because it will try to bring back this block in its equilibrium position. Now spring force is what? This spring force is a variable force, and it is conservative in nature. Conservative means that the work done due to this force depends on the this initial and the final position of the object. Now the spring force which I have denoted here by Fs, is directly proportional to displacement, and so it can be written as that Fs is equal to minus kh, where k is called the spring constant, and I have put this minus sign here because the direction of the spring force and the displacement is opposite. In the figure number 1, you can see here that when this block is displaced along this positive x direction, the spring force is acting in the negative x direction. That is, the direction of the spring force is negative to the direction of the displacement. So therefore Fx is equal to minus Ks, where minus sign indicates that Fs is the direction of Fs is opposite to the direction of displacement. Similarly, in this figure number 3, here also this this block is compressed. This block is compressed. So when this block is compressed, the spring force will act in the positive x direction. This is the positive x direction, so that in order to bring this block in the equilibrium position. And here the displacement is occurring in the negative x direction, and the spring force is acting in the positive x direction. So spring force is given by Fs is equal to minus kx, where k is the spring constant, where k is the spring constant. Now let us consider that this block is displaced by xm along the positive x direction. So if the block is displaced along this positive x direction, so in this case the work done by the spring force is given by this is the origin, the displacement is xm, So I will be integrating from 0 to xm, and it will be that is the this spring force into. So spring force is equal to effect. This is equal to minus kx dx. Okay, where this minus kx is basically the spring force. So the work done by the spring force is will be given by this integration of from 0 to xm, where 0 is the its equilibrium position and xm is the displacement, kx is the force. So kx, so basically this is I can just write it like this: fs dx, and this can be written as 0 to xm minus kx dx. And now this k is a constant. This this is the spring constant, which is a constant value for a particular spring. This k so now I will be just writing minus k is outside, and I will be integrating x dx from 0 to xm. So this will be equal to minus k. This will be equal to x square by 2, and it will be from 0 to xm. So this will be equal to minus 1 by 2 k xm square. So the work done is equal to minus 1 by 2 k xm square, where xm is the displacement of the spring. So here I can write down here, or you can simply write it here now. Let us say here, that is the work done is equal to minus 1 by 2 k x square, where x will be the displacement of the spring. Now in the previous session we have seen that the potential energy is equal to the negative of the work done. That is in the session number 7. Since the change in the potential energy is equal to negative of work done, therefore the potential energy of the spring, the potential energy of the spring will be equal to 1 by 2 k x square, where x is the displacement of the spring. So the work done is equal to minus 1 by 2 k x square, and the potential energy of the spring will be equal to 1 by 2 k x square, because the change in the potential energy is equal to the negative of the work done. So there are three important formulas here now. That is, spring force is equal to minus kx, where k is the spring constant and x is the displacement. The potential energy of the spring is given by 1 by 2 k into x square, and the work done is equal to minus 1 by 2 k x square. Here x is the displacement of the spring. Now here this minus sign is coming here because because here you can see that the spring force, the direction of the spring force is opposite to the direction of the displacement. So these are the three important formulas. This is the first one, then this is the second one, and this is the third one. Now, so I will be writing here, that is the potential energy of the spring is equal to 1 by 2 k x square, and the spring force is equal to minus kx. So these are the three important formulas with relation to the topic of spring force and potential energy of the spring. Now here we have taken two assumptions, that a spring is massless, and the second thing is that this block is lying on a smooth horizontal surface, that is, it is lying on a frictionless surface. So these are the two assumptions which we have taken in order to derive these equations. Now, this is the equilibrium position in the figure 1. The figure 1 shows the equilibrium position of this spring block system. Now let us consider the figure 2 here. So when I am extending, when this block is getting displaced by, let's say, xm here, so and let us consider that this block is released from this point. So what will happen? This block will, this spring force will bring back this block to its, will try to bring back this block to its equilibrium position. Now at this, now we have also seen that the sum of the, that is the total mechanical energy of a system is constant. So we have studied about it in the session number 7 also. So here, if the total mechanical energy of a system is constant, so at when this block is at this position, that is when it is displaced when by xm, then at this position it will be having only the potential energy, which is given by half k xm square. But now when it is released, it will be now this is the total mechanical energy of this system when this block is displaced by xm. Now when it is released from this position, this block will this spring force will try to bring this block back to its equilibrium position, and this block will attain the maximum velocity when it has reached the equilibrium position. Okay, and second thing, first thing is that this block will attain the maximum velocity at this equilibrium position, and second thing is that when this block is released from here, from this point, that is when it is displaced by xm, then this energy will partly get converted into kinetic energy. So at any moment of time, this energy will be equal to half m v square plus half k x square, where x is the displacement at any moment of time and v is the velocity of this block. Now, since I have just told you that this block will attain the maximum velocity when it reaches the equilibrium position. So when it attains the maximum velocity, it means that this energy, that is this equation can be written as half k xm square is equal to, because at this point this energy is getting totally converted into the kinetic energy. So this will be equal to half m vm square, where vm is the maximum velocity of this block. So from here this half will get cancelled out, and the maximum velocity of this block will be given by k by m xm square, or we can say that the maximum velocity of this block will be equal to root k by m into xm. So this is also a very important formula, that is the maximum velocity of this block will be equal to under root k by m. K K is the spring constant, xm is the displacement of this block, and m is the mass of it. So now, so the most important thing here is the total mechanical energy of a system is constant. So based on this, I have written this formula, that is this when the block is displaced by, say, by a displacement xm, then it will be having the potential energy, which will be given by half k xm square, because here the kinetic energy is 0. But when it is released, then this energy will be getting converted partly into the kinetic energy also, and the rest. So here when this block is released, then half k xm square will be equal to half mv square plus half kx square. Now this is the value at any moment of time when this block is released. Here x is the displacement, okay, and v is the velocity of that block at this displacement. So this equation, from this equation, I have also calculated the maximum velocity of this block, considering the fact that this block will attain the maximum velocity when it reaches the equilibrium position, that is this point O. So at this point, this entire potential energy will get converted into the kinetic energy. Okay. So if this half k xm square will be equal to half m vm square. Now here vm is what? This is the maximum velocity of this block when it is released after getting displaced by a displacement of xm. So here xm is the displacement and vm is the maximum velocity which this block will achieve. So this is the maximum velocity, that is vm square is equal to k by m xm whole square, and vm is equal to under root k by m into xm. So this is another important formula. So we have now got these four important formulas, that is vm is equal to root k by m into xm, where xm is the displacement, k is the spring constant, m is the mass of the block, and vm is the maximum velocity. Work done is equal to minus half k x square. Potential energy will be equal to 1 by 2 k x square, because the change in the potential energy is the negative of the work done. So this negative sign will not be there in the case of potential energy. So potential energy is equal to 1 by 2 k x square, and spring force is equal to minus kx. Minus sign indicates that the direction of the spring force is opposite to the direction of displacement. So thank you very much for joining this session, and in the next session I will be coming up with a numerical problem based on this topic. So till then, have a nice day. Bye.